Yeah. So go ahead. You can ask me questions. So this course on numerical methods and simulation techniques for scientists and engineers, it's a course that, I mean, similar course also exists in the MOOCs platform, but this course wants to do more than that. In fact, one of the main motives of this course is to amalgamate questions from both science and engineering. And as you might have seen that there are a number of questions which are purely of mathematical interest, and there are also physics problems. There are also problems from other engineering disciplines such as, you know, maybe chemical engineering, maybe civil engineering, and that's how the course is actually planned. And these course would be, you know, relevant for the engineering disciplines as well. And in addition, two very important simulation methods have been presented, and they are the Monte Carlo simulation and molecular dynamics, and at least shown that how they could be useful in solving problems related to different areas of physics and sometimes engineering. So these are of course simulation techniques, and they are not restricted to any particular discipline, but this Monte Carlo is very widely used in physics problems such as Ising model, where one sees a phase transition as a, you know, function of maybe temperature and things like that. And the molecular dynamics really simulates the trajectory of atoms and molecules in different force fields. So these are nice and simulation techniques that one needs to learn, and as I said many times during the course as well as today, that this will have you know, ramifications across different areas of science, engineering and other fields as well. We have studied right from the beginning. We have studied you know, finding roots of equations, and we have started with very simple problems which can be done without the help of a computer, and introduce methods such as bisection method and Newton-Raphson method, secant method, etc., and have very importantly discussed the errors associated with each of these methods and how the errors grow or die out as we carry on different iterations. And then we have talked about interpolation methods, and there is a question on interpolation. The question was that whether interpolation or regression, which one is more accurate. And in fact, I have not thought about it, neither, you know, a sort of books would clarify this, I believe. But it's a good question. So to answer that question, I would believe that if you have a smaller number of data points, then you can do a regression which would have more clarity and accuracy. Whereas if the number of data points become large, then you can do interpolation, use the interpolation technique. And usually in science or engineering, we talk about a large number of data points. So keeping that in mind, I think the interpolation, particularly the Newton's interpolation, I have already told you that the Lagrange's interpolation requires you to calculate all the coefficients all over again as you increase one more data point into your file, whereas the Newton's doesn't require that. So Newton's interpolation scheme is definitely a good one. And then there was another question on we'll come back to the question. Let me sort of also say that let me take the question. So it says that so the bisection method and Newton-Raphson method, this question was asked earlier to me, and somebody who had asked that question is really has thought about it, and in fact the stopping criteria is not taken as a function going to 0, but you can take in the sense that it will not have any significant accuracy problem if you take the function acquiring a value around 0. So, you give a tolerance of 10 to the power minus 3. So, if the function becomes 0.001, you use that as a stopping criterion. But as I said that it is not the value of the function, rather the value of the roots between two successive iterations is used. But I believe as the question or the person who asked the question, I think wanted to know particularly about the function being close to 0, and it could be used. I don't believe that there would be any loss of accuracy there. We went ahead to do the numerical differentiation after that, which we have said a number of times that it's not a good idea to do numerical differentiation, because every time you undertake that assignment, you will have to divide things by a number which is very close to 0, and dividing by 0 is a risky business in computers. However, sometimes to find velocity or acceleration from the trajectory of particles, we need these calculation of derivatives and maybe even sometimes double derivatives and so on. So, they had to be done, but with caution. We have also done numerical integration. This is one of the nice things about numerical methods, is that you don't have to know the nature of the function. You don't have to, you simply have to have the data points, and then using Lagrange's or Newton's interpolation formula, you find out the function and that you integrate. And numerical integration can be easily done by using, say, Simpson's 1/3 rule, Simpson's 3/8 rule, and maybe other Richardson extrapolation, etc. And it's a fairly accurate method with no great accuracy problem or errors, provided you have the data points chosen to be very close to each other. However, if the data points are far away from each other, then you could be missing some variations in the function which you are trying to integrate. Other than that, it's fine. Numerical integration is a well established method. Then we went ahead to talk about differential equations, and particularly eigenvalue problems and initial value problems. And there we have talked about really the general solutions and particular solutions. I saw some questions on general solutions and particular solutions, and they are basically, when you have a solution of a differential equation, it could give you actually a family of solutions which is called the general solution. When you further apply the initial value condition or the boundary value condition, we can reduce that constant or the family of solutions to one particular solution, which is called as a particular solution. And we have done a number of methods, such as Euler's method, Hume's method. Runge-Kutta method is the most commonly used method. Runge-Kutta, that has a second order Runge-Kutta or a third order Runge-Kutta, fourth order Runge-Kutta methods. These are used mostly to solve differential equations with initial values being given, or the boundary values being given. And then we went ahead to do this simulation techniques, and initially the Monte Carlo is used as an numerical integration tool, where the data points are not chosen in equal rather equispaced intervals. One can choose them randomly, and these random variables can define those points, which we have done it by otherwise by Simpson's 1/3 rule or 3/8 rule. And these are finding the value of pi using a circle that is inscribed within a square can easily be found out and demonstrated, the utility of this method. But of course, in civil engineering and in chemical engineering, they are used for finding out all these rate of failures and so on, and which you will find that there are problems related to that in your assignments. And then finally, we have done the molecular dynamics, where we have clearly said that these are required to solve equations such as Newton's law of motion in order to find the trajectories subject to a particular kind of potential, which could be intermolecular potential or interatomic potential, such as Lennard-Jones potential and so on. And these are certainly sort of good techniques for us to learn and get used to, and these are quite useful as well in actual real life problems in both science and engineering. Any questions that you have? You could ask about anything. Most of the questions that have been raised throughout the course have been answered either by the TAs of the course, or we have jointly answered those. The only thing that's beyond our control is if you do not submit the assignment on time and the portal gets closed, then even if we have intention of taking those assignments for evaluations, we can't do that. Okay, so some of the people who could not submit it on time, in spite of our best intentions, it could not be taken at that time. So I hope you understand that. If you have questions regarding even the nature of exams, etc., you could ask, but we prefer that you stick to the technical questions regarding the course. So I hope you are enjoying the course, and very importantly, do not ignore the error calculation that have been told during the class or rather these lecture hours, and also they have been emphasized upon significantly during your during the assignments, or rather in the assignments. So there you find that particularly if you are an engineer, say a civil engineer, the error margin is quite less in terms of building constructions, etc. I mean constructions of dams, bridges, buildings. There if you have to solve an equation, and there the error that you commit is more, then it becomes it's a faulty construction. So sometimes the errors become so important, and we also need to understand that the error really propagates from one iteration to another. So if it becomes an uncontrolled propagation of error, that is going to be a big problem in any calculation. Okay, so we need to keep those errors in the way that they converge, and probably they converge to infinitesimally small value after say 100 iterations. However, you do not have the privilege or the luxury of doing 100 iterations for a given problem because it could be very time consuming, or because it could be computationally very expensive. So in which case you probably only do 50 iterations, but at least you know that that has a converging trend and not a diverging trend. Sometimes most of these problems close to phase transition, or close to what we called as in the boundary of one phase to another, say a liquid to a solid phase or a solid to a gaseous phase, the quantities they fluctuate randomly, and that causes a lot of problems in terms of convergence. So in one iteration you see that the convergence is coming, and after a while you could see that there is no convergence there, and this really happens in a simulation, particularly the Monte Carlo simulation that's applied to Ising model. Close to the phase transition from a paramagnetic phase to a ferromagnetic phase, you see that the order parameter, which is the magnetization in that case, is a fluctuating quantity, and it fluctuates heavily close to the phase transition, and so one has to really wait for a long time as compared to when it's far away from equilibrium or far away from the phase transition. So these are some of the important points that you should keep in mind. I believe I haven't gotten any question as yet. Please ask if you have any question. So I believe there are no questions because either people haven't joined, but in any case you are posting questions, and most of the questions have been answered either by the TAs or me. So keep posting questions, and as you have, we are into the something like 5th week, right? So you have two to three more weeks to go. So if you find that these simulation techniques which are going to be taught after this, if you find any questions, you could definitely ask me. Right now, I mean, in view of the fact that there are not any question, there's no question at all so far, we got to hang up and call it a day. But if you have further questions, if you find that you haven't understood something, please get back to us via that portal. Right.